In this chapter, we talk about plane stress and plane strains. The motivation of such kind of arrangement is this. The cause of elasticity try to deal with two-dimensional and three-dimensional problem. Okay, between two-dimensional and three-dimensional problem, which one is the more simple problem? Of course, 2D, two-dimensional is more simple than three-dimensional problem, right? So, for the beginner, they should learn a simple problem to start instead of difficult problem. So this is why we introduce two-dimensional problem to you in this chapter, okay? And I want to mention that there are two different situations where useful two-dimensional problem arise. One is plane stress, one is plane strains. Let us study these two problems, these two kind of problems one by one. And in 2.1, section 2.1, we study plane stress first. I must address that plane stress is a terminology to describe some special problem for the thin plate. Okay, in this picture, we have a thin plate, and the important point is, on the surface of the plate, there are low stress components, sigma zz equal to sigma xz equal to sigma yz equals 0 on the surface. Moreover, because the plate is so thin, okay, and on the surface, these three components are 0. So inside the plate, these three components will approximate equal 0 because the plate is so thin, and on the upper surface and lower surface, these three components are 0. So inside the plate, it is very difficult to develop non-zero stress. So we say that these three components, sigma zz, sigma xz, sigma yz, approximate equal 0 within the plate. Okay. Such kind of simplification will give us a lot of convenience when we try to solve problem. Okay, the mechanical problem will be much more simple with such kind of simplification. And also at the edges of the plate, the normal stress sigma xx and sigma yy not equal 0, and also the shear stress are not equal 0, which can be written in this way. And also all these three stress components are not depend on Z2. Why? Because the plate is so thin. So these three components behave just like constant along the Z axis. Okay. We say that these three stress components do not depend on the Z coordinate. We summarize the whole situation in this matrix. Okay, the stress tensor, which is three times three dimension. Instead, in fact, have only a small matrix embedded inside, which is 2 by 2, right? This small stress matrix is 2 by 2, even though the whole matrix is 3 by 3. Okay. Let us look at the strain component below. The strain component will have some simplification too. Why? Because the shear component, sigma xz and sigma yz equals 0. And then according to the Hooke's law, the shear strain absolute xz and absolute yz are also 0 too. So we write these two conditions here. And now, how about the component absolute zz? Let us look at this. According to the three-dimensional stress-strain relation, we have sigma zz equal to this one and equal to this one. Now, sigma zz equals 0, okay? Here, sigma zz equals 0, okay? Sigma zz equals 0, okay? Approximately. So, this one equals 0. It means that absolute zz and absolute xx and absolute yy are not independent to each other. They are related by one mathematical formula. So we use this mathematical formula to solve absolute zz. Like here, we move it to the left of the equality and then divide this material constant by this one to get this relation. Okay, so from this relation we can have this relation. This relation tells us that absolute zz can be computed from absolute xx and absolute yy, and in general, absolute zz is not 0. Okay, let us summarize our result here. The absolute the string matrix, which is 3 by 3, you all have 4 0 components here. Okay, these 2 and these 2. Okay, but the normal string in the z direction, absolute zz, not equal 0. This is absolute zz, and it is not equal 0. Okay, this one is a little bit different from the stress tensor, stress matrix. See, in the stress matrix, all these components along the edges are 0. Okay, but for the string component, for the string matrix, only these 2 and these 2 components are 0. The normal string absolute zz not equal 0. Okay, and also let me look at the symbol here. Little e stand for here. Little e stand for absolute xx plus absolute yy plus absolute zz, and absolute zz can be replaced by this formula. Okay, so we can replace this absolute zz by this one. Okay, we just take this over here. Okay, and then we see that this little e can be expressed as absolute xx and absolute yy times a constant, because we can correct terms to have this result. So the little e symbol can be expressed in this way, and this absolute xx plus absolute yy can be defined as another little e with a star, e star here. So little e is depend on little e star by this relation. Okay, and little e is absolute xx, absolute yy, absolute zz summed together, and little e star is absolute xx plus absolute yy, and they have a proportional relation like this. Okay. Let us summarize our result here. The stress-strain relation in general, as a 3 by 3 matrix stress, 3 by 3 stress matrix related to the 3 by 3 string matrix like this. But now for plane stress situation, we have some components are equal 0 here, and some components are equal 0 here. So we can see that even though the outlook are 3 by 3, but these matrices are in fact 2 by 2 matrices, right? Only this little matrix inside is important, and only this little matrix inside is important. So we would like to construct the relation between this little matrix and this little matrix. Okay, So means that we want to construct a relation between this strain component and this stress component. Okay, let us see how to carry out such kind of calculation. Remember, we have a set of three-dimensional stress-strain relation like this. Okay, we have already talked about this stretching relation in the previous chapter. Okay, here absolute xx equal to 2 mu times absolute xx, sigma xx equal to 2 mu times absolute xx plus lambda lead to e. And now lead to e can be replaced by this relation. 2 mu over 2 mu plus lambda times E star. Okay, this relation has been mentioned before and we rewrite it here. Okay, let me explain to you in front of the screen. This little e can be replaced by this one, which can be written as like this. Okay, and we define a new constant lambda star as this one. Okay, so by writing such kind of new symbols, we can say that absolute xx equal to 2 mu absolute sigma xx equal to 2 mu times absolute xx plus lambda star times E star. Okay, write the line here. In the same way, absolute sigma yy can be rewritten in this form, but be careful. I had made some mistake. Please change this absolute xx to absolute yy. Absolute yy here. I make some mistake. Absolute yy. Okay, and we write this relation to here. And also sigma xx equals 0, so we don't need to write it down. And also we have this sigma xy equal to 2 mu absolute xy like this. See, in general, for a three-dimensional stress strain relation, we have 1, 2, 3, 4, 5, 6 equations. Now for the plane stress situation, okay, we have a set of 3 equations only, 1, 2, 3. Understand? And also, very important, the outlook, even though the numbers are not the same, but the outlook of them are the same. See, the outlook here for the three-dimensional stress-strain relation like this can be replaced like this. Okay, and this one look pretty much the same. See, little e is written as like this, and little e star is written like this. Okay, so they have a very similar outlook. Okay, so even though the number have been reduced from 1, 2, 3, 4, 5, 6 to 3, but the mathematical structure of the normal stress and normal strain relation are the same. Okay, and the shear stress and shear strain relation is the same too. Okay, so we can memorize such kind of relations very easily. If you can memorize the three-dimensional case, of course you won't miss the two-dimensional case, because this one and this one just look like the same. Okay.